start recording, and hopefully that will be clear now that we are recording. Yes, I can see a little flashing red on top of my screen. I can see a little flashing red button telling me that I'm recording. So folks, from now on I am recording. So behave, no bad language, please. So these are my objectives for today and for all these sessions. Essentially, I want to share some ideas with you. I work at the moment at the King's Maths School, which is a specialist sixth form state, but specialist sixth form in Lambeth in South East London, for students who are high attainers in mathematics. The curriculum is a very focused curriculum. All our students study maths, further maths, and physics, and then either economics or computer science. And the goal is for them to proceed from here to STEM subjects, mathematics or engineering, or natural sciences, and we have a particular commitment to increase diversity and representation in those areas at university, from hitherto unrepresented populations. So we have a very good gender split, we have a very good ethnicity split to reflect our area, and we do a lot of work to make sure people, our students from disadvantaged backgrounds are able to apply. So, sorry, every time I pause, it's just because I'm admitting somebody. So at the moment, I can't tell you this is what I am teaching my year 11, because I don't have a year 11 at the moment. I'm only teaching year 12 and year 13 at the moment. But I've taught year 11 for probably about 20 years. I've taught since 1997. And so I have taught a lot of year 11s, and I've taught some very, very high attaining year 11s. I've taught in selective schools, both state and independent schools. And so these ideas are drawn from my experience doing so. So these are very much things I would actually use in an actual class with actual year 11s if I actually had a year 11 class tomorrow to go and use them in. So I hope you like them. I hope they inspire you. I hope some of them intrigue you, and I hope that when you share them with your students, they infuse your students. I've been teaching for 20 years, and therefore anything which is really good is probably not my own idea. It's probably something I've developed collaboratively with my departments, or possibly just stolen from somebody else. Anything you think that was a bit rubbish probably was my own idea. So credit where it's due to all the people I have worked with over the years, who are far too numerous to mention because I'm really old. I know you're not NQTs, but if you were NQTs and you're asking me kind of what's your advice for teaching a top set, I'd say the following. Actually, I would say this applies to teaching any set. This applies just as much to teaching low attainers. I've taught children coming into secondary who are way below expectations, who are working at P levels, not even at national curriculum and end of primary school expectations. So I think these principles apply to all classes, but I think they especially apply to top set classes. And my sort of catchphrase is get the maths from them. So it's ask them questions, don't tell them stuff, don't tell them facts, don't tell them results. It's ask the questions. So when I'm designing my lessons, and as I say, when I'm designing lessons for any class, but especially when I'm designing lessons for higher attainers, as I am at the moment at the King's Maths School, my lesson plan is basically a sequence of questions. What do you notice? What's the same? What's different? Which might be the odd one out? Do you think this is always true, sometimes true, or never true? Do you think this is always possible, sometimes possible, never possible? Just here's a statement, agree or challenge, true or false. Are you sure? How do you know? Can you give me another reason? Can you give me another example? Can you give me another method? Can you give me another diagram? Can you give me a non-example? What do I mean by that? Well, Pythagoras, so 3, 4, 5 is a right angle triangle. 5, 12, 13 is a right angle triangle. 3, 4, 6 isn't a right angle triangle because it doesn't satisfy Pythagoras. So a quadrilateral with angles of a quadrilateral with opposite angles that don't add up to 180 is not cyclic. A triangle which is not right angled is not got one side of it being the diameter of a circle. So the converses of the circle theorems. And I think we do a lot of examples in our teaching. I'm not sure we do enough non-examples. Again, thinking about A level at the moment, thinking about this is a solution of the equation. This is not a solution of the differential equation. And then lastly, make up your own, which sounds like such a cop-out, saying to the kids, oh, you make up your own questions. You answer each other's questions. It sounds like you're being really lazy. You're not. It's a really good task, because if the students can make up their own questions, make up their own examples, they really understand what is going on. Producing mathematics is much harder than receiving mathematics. So if they can make up their own examples, then they really do understand what is going on. If I was to kind of sort of summarize it, I'd say you're trying to do 3 things, again, with any class, but particularly with a top set class. You're trying to develop their procedural fluency. You're trying to enrich their conceptual understanding, and you're trying to embed and make secure their factual knowledge. They need factual knowledge. They need to know that something is the case. They need to have fluency. They need to know how to use it, and they need to have conceptual understanding. They need to know why something is the case, and to tie it all together, they need to know when to use it. And it's pulling those bits together that you're trying to do all the time through these questions as you try to get the maths from them. And I'm going to, over these sessions, I'm going to try to illustrate it and use these questions, these prompts, so you can see how I would use them, and that might inspire you and share with you to use them yourself and share with your colleagues. So think about sequences. I thought about the following. I thought about sequence generating rules. I thought about comparing sequences. I thought about Möbius sequences, which may be a term unfamiliar to you, but it is Möbius as in Möbius strip, but it's not the same thing. And then I thought I think about functions, because we think a lot about sequences of numbers. We do a lot of work on arithmetic sequences of numbers, quadratic sequences of numbers. Do we do that much work on sequences of functions? So I'm going to come to that towards the end. So what do I mean by a sequence generating rule? So a sequence generating rule might be something like a term-to-term rule. So start with 3 and keep adding 4. So I'm going to start with 3. I'm going to keep adding 4. So 3, 7, 11, 15, 19, and so on. So that's a term-to-term rule. I'll use that abbreviation later. Term-to-term, a term-to-term rule. The value of one term is given to you by the value, well, in this case, of the preceding term, but it could be the preceding terms, plural, like the Fibonacci sequence is term-to-term, but really it's terms-to-term, because the sum of 2 terms makes the next term. Or it could be a position to term. So it could be position to term, could be position to term, where the value of the term is given as an expression in terms of, as a function of its position in the sequence. So the value is 4n subtract 1. So the first term is value 4 times 1 subtract 1, which is 3. The second term is 4 times 2, which is 8, subtract 1, which is 7. The third term has got a value 4 times 3, which is 12, take away 1, which is 11. The fourth term is 4 times 4, take away 1, which is 15, and so on. Oh, look, they're the same. Oh, they're the same. So what's the same, what's different? We've got that they're different rules. One's a term-to-term rule, one's a position-to-term rule, but they generate the same sequence. Notice I don't say the value of the nth term, which is often the phrase you see in books, often the phrase you see in exam papers even, and often the phrase you hear the children say. And I don't say that, and I would encourage you not to say that. Essentially, because what does it mean to say the value of the nth term equals 4n subtract 1? 4n subtract 1 isn't a value; it's an expression, and it's an expression for the value of the nth term. And also, what does the nth term mean? Well, in particular, actually, so I was just thinking, actually, even worse than that. Of course, sometimes people don't even say the value. They just say the nth term. And that really is awful, saying the nth term, because what does that mean? The what of the nth term is the position of the nth term, the value of the nth term. So I don't like the phrase the value of the nth term, because I think the nth term is not very clear. I think saying position number n or the nth position is better. And I certainly don't like the nth term, because how can an expression be the nth term? It represents the value of the nth term. So I do always use the full phrase, the value of the term in position number n, or I suppose I sometimes say the value of the term in the nth position, but I certainly wouldn't say the nth term is, because this is an expression. Okay, so a bit of mathematics for you. Here are a couple of sequences. What do you think the seventh term is, and what do you think the sequence generating rule might be? So I'm going to give you just a couple of minutes to have a think about that. What do you think? What do you think the value of the seventh term would be? Suggest a plausible value for the seventh term, and what do you think the sequence generating rule might be in words or in symbols? And also, I mean, obviously, I realise these are quite obvious for you. What's the point of the question? Why do you think I've thought of these questions? What am I trying to draw out from the students by these questions? So, just kind of a couple of minutes to think about that. Really, not so much what the answer is, but why did I choose these? Hold fire answer just for a moment. Claire, you've made a good point in the chat, but you sent it just to me, not to everybody. Do you want to resend it to everybody? I mean, I agree what you say. So doing these sorts of things online, using the chat is great. But more than just asking questions where they give answers in the chat. I mean, these particular questions. Why have I chosen these two sequences? I suppose is what I'm asking. What might your students do, and what would you want them to do? Well, so to the answers for the 7th term of the first one, I certainly was thinking of 45, and for the 7th term of the second one, I was definitely thinking of 81. So I'm happy for people to disagree with me on that, but that's sort of what I was thinking of. Now, how would your students do that? Well, they probably look at the method of differences. Thanks, Claire. Thanks for sharing that with everyone. And that's a good point you've made there. They probably do the method of differences. I just need to make my chat slightly different size so I can see it. I've made it slightly too wide. Oh, that's better. So now I can actually see it on screen along with everything else. Yes, exactly. So Claire, I completely agree with your second point. Well, sorry, so I agree with both your points, but particularly with your second point, which is to recognise that that in the second sequence, these are the square numbers. But then what do they do? What do they do? They then just write n squared there because they think, oh, square numbers. Oh, right, so it's n squared. And they don't recognise that these are the shifted square numbers. So they need to stop and take a step back and go, well, actually, it is basically the square numbers, but I'm not squaring 1 to get the first term. I'm not squaring 2 to get the second term. I'm not squaring 3 to get the third term. And so they need to take a step back and realize what they're actually squaring is the position plus 2 to get the value. And it's that sort of little complexity which I think makes activities like this really worthwhile, because they go, oh, they sort of jump to the answer, it's square numbers then squared, and they don't take a step back and think, what does the n mean, and does that work? And then a really nice point there from Jenny, if I may say. So thanks Jenny. So that they look at the differences. So they look at, so I'm going up, say the second one, I'm going up, I had a 7, I had 9, I had 11, or the first one, I had 3, I had 5, I had 7. And they look at the differences, they go to the differences, they don't take a step back and think, well, the fact that the differences are increasing tells me this might be quadratic, let's think about the square numbers. Suggestions then for the first one? So now that you know I'm thinking square numbers, does anyone want to suggest where the first one has come from, just out of interest? It's related to the square numbers. That's what I was thinking of, Claire. Thank you. Yeah, I was thinking of n squared subtract 4, and thanks Henry too. So my experience of particularly picking up a set in year 11 is often they've been taught a procedure how to find the nth term, to use that phrase, how to find an expression for the value of the nth term, to use a better phrase, for a quadratic sequence. They've been taught a procedure, but in the process of doing that, they've lost the sense of actually taking a step back and going, well, let's look at the square numbers. What are the square numbers? Oh, the square numbers are 1, 4, 9, 16, 25, 36. Oh, what have I got? I've got the square numbers reduced by 4. So they've lost that feel for the sequences. They've lost that if you like bigger picture. They go to procedural fluency really quickly, and they don't sort of take that step back and sort of survey the territory. So these two now 1, 3, 6, 10, 15, 21, they're supposed to recognize those as the triangular numbers. So triangular numbers are supposed to be a known fact. So it might be worth checking the students do actually know those, and do they know why they're called the triangular numbers? Do they know they can make some triangles, snooker balls out of them? So do they know they're called triangular numbers? Do they know why they're called triangular numbers? And then once they've done that, and then obviously that's 28, and then they are supposed to know the formula a half n plus 1, or you can derive that. But let's say you've recapped triangular numbers. So what's happening with the second sequence? Well, can we see the connection? it's basically the triangular numbers take away 1. It's 1 less than the triangular numbers. Or, that's really nice, Claire. I hadn't thought of that, Claire. Thank you, Claire. I hadn't thought of that. That's not how I built it. So I built it as you can see on the screen, shift back and subtract 1, whereas Claire is actually saying another way of doing it is that you let's do a different color. Is actually add on something. And so therefore that would be 35. So that would be lovely, because that means we'd have to, so half the class would perhaps approach it from Claire's way of thinking about it. So they would say it's a half n plus 1 plus n. And then the other half of the class, hopefully, would approach it from my way of thinking about it. But I think they would make the same mistake. So I think, as I described earlier, so I think they would say that. So I think they go, oh, triangle numbers take away 1. And they would use the general formula for the triangle number, take away 1, and they won't take into account the shift. They won't compensate. So it's not that, it's the next one up. It's n plus 1, n plus 2, subtract 1. You've got to go to the next triangle number up and then subtract 1. And then, of course, you've got a lovely bit of algebra. Are those the same? So question mark. Are those the same as each other? Is a half n plus 1 plus n the same as a half n plus 1 n plus 2 subtract 1? And it would just be great, wouldn't it, to have some children saying it's the blue answer, some students saying it's the red answer, and then have a heated debate about who's right and discovering actually it's the same thing. So the idea, I think, what I wanted to suggest to you was this idea of shifting sequences and really get them to think about what the notation means. That it's not just any old n you bung down. You've got to think about how it relates to the position in the sequence. And then actually, thanks for that really lovely suggestion, Claire, of another way of approaching it. And then, of course, you get all the algebra coming out, agree or challenge. What's the same? What's different? What's happening here? Well, we've got some doubling going on here. You can see some doubling happening there, etc. You can see some doubling. And so presumably that's going to be 384. And so what's going to be happening here? Well, doubling, so something like powers of 2. But again, powers of 2 don't work because powers of 2 would give you 2 and 4 and 8, not 6 and 12 and 24. So we have to have 3 lots of power 2 to the n. And then, of course, somebody's going to say, is that 6 to the n? And that's obviously worth unpacking why that's not the case. And then what's happening here? What's happening here? So we've got sort of times by 5, times by 3, times by a bit less than 3. So it's not geometric. I should have used that word a bit earlier. Obviously, that's a geometric sequence. So, kind of what's happening here? It's not geometric. It's if we sort of look at the differences, then that's 10, and that's 20, and that's 38, and then that's 10, and that's 18. So we haven't got. It's not quite a quadratic. So now obviously they could continue the differences, but again, it's about thinking, certainly in the context of GCSE, it's thinking about what sequences am I supposed to know? You know, it's not geometric, it's not quadratic, it's not the triangle numbers. What might it be? I'm up for any suggestions. If I give you a clue, he says, working out quickly the last one, I'm going to say the last one there is 350. So what sequences are they supposed to be familiar with? Supposed to be familiar with linear ones, supposed to be familiar with quadratic ones. They're also supposed to be familiar, thank you, Keith, with cubic ones. And so I built this as n cubed plus n. But sequences like this and these sort of examples, the idea is not to get them to practice a formula, practice a rule. The idea is to get them to think about, well, what else do I know which goes up pretty rapidly? Oh, cube numbers go up pretty rapidly. It's not as rapidly as doubling. That would get much bigger, much quicker. But what else do I know which goes up quite rapidly? Oh, cube numbers. Okay, let's try the cube numbers. And it's that sense of experimenting, experiencing number sequences that I'm trying to get across through these sorts of questions. So then we come to something like this. So let's look at the bottom one first. Fibonacci sequence. So straight away, seventh term is a value 13. But what's that? Now, I mean, you may know there is a formula, there is a position to term rule for the Fibonacci sequence, but it's incredibly complicated. It involves square roots of 5 and square roots of 2. And so the really point of this activity is to get the students to start to realize that sometimes it's really easy to work them out term to term, but really hard to work them out position to term. So these ones we've done so far, they're probably equally straightforward term to term, position to term. When we come to Fibonacci, the term to term is really trivial. It's just adding up numbers. The position to term is incredibly complicated. And you might want to set them to go and do a bit of research and find out about it. But it's really getting to realize that just because you can write a term to term doesn't mean you can write a position to term. And that's what this example is for as well. So what do we have here? Well, presumably the answer is 2. I mean, that would seem to make sense, wouldn't it? So how are we going to describe that? How are we going to say it goes 257, 257, 257, 257, 257? How are we going to get the students to say that sort of those ones all map to 2, those ones all map to 5, those ones all map to 7? Well, they're going to need to think about what they mean by those ones. And of course, they might recognize, hopefully not recognize, being high retainers, that 3 and 6 are multiples of 3. And so they might start thinking, well, it's got something to do like multiples of 3 map to 7. And then how would they describe the green numbers? Well, they're 1 less than a multiple of 3. And then what about the red numbers? Well, perhaps they're 2 less, or perhaps they're 1 more than a multiple of 3. And I find, my experience is that students find going from even and odd, which is multiple of 2 and 1 more than multiple of 2, to other situations like multiples of 3, 1 more than multiple of 3, 2 more than multiple of 3, really hard. They've got very used to the idea of the dichotomy, even or odd, and the idea of a trichotomy, multiples of 3, 1 more than multiple of 3, 2 more than multiple of 3, is a big conceptual step. So that's why I think questions like this are worthwhile, and therefore your sequence generating rule, so your position to term sequence generating rule will have 3 different parts to it. If n is this, then this. If n is this, then this. And if n is this, then this will be my answer, 2 or 5 or 7. And that's what I mean by, if you look back a couple of slides, I said my sequence generating rules could be term to term, position to term, or something else. You see, and now we see we're starting to get into the something else territory. Either of these ones, I'm going to give you a couple of minutes to have a look at either of these ones. I'm interested in your suggestions, what you think the next term might be for either of them. I mean, I think the answer for the bottom one is quite obvious, but how would you say it, or not how would you say it, but how do you think your students would say it, or what would you want them to say? So I'm going to go quiet for a couple of minutes and let you think about what you think your students would say in response to these. I think you get a lot of that, exactly. Someone just put in the chat 9 to the power n. I think absolutely they'd see the 9s, and they'd sort of say n 9s, and they go like 9n, but that's 9 times n, and they wouldn't know how to say it. So that would be lovely. So some nice ideas coming through. So 10 to the power n subtract 1. That's what I'm thinking of. Do you reckon your students would see that? Do you reckon they would think, oh, I see, it's 10, it's 100, it's 1,000, it's 10,000, etc. It'd be really interesting to see whether they spot that, the idea of these numbers. What are they? They're all 1 less than a base value, than a place value. Tens, hundreds, thousands, 10,000s, etc. And therefore they're all less than a power of 10. See, I reckon you would get quite a lot of the term to term. So what's the term to term rule? What's the term to term rule here? It's basically, add on another 9, because it's not that mathematically. You're not adding on 9 at all. It'd be interesting to know if they could articulate the term to term rule, which is basically shove everything up and write an extra 9 in. So 9 turns to 99, and 99 turns to 999. So it's move everything up the place value chart and then insert an extra 9, and then it's something like that, isn't it? Yeah. So it's, thanks Henry, it's sort of something like times by 10 and then add 9, times by 10 and then add 9. So something like that would do it, and then again, it'd be interesting just to see, well, you know, can we who thinks who gets the position to term, who gets the term to term? Can we marry the two together? Am I drawing a veil of silence over the first example? Anyone suggest an answer for the first example? This is one where there is a very straightforward position term, and well, as you see in a moment, there is basically no term to term rule. Let me give you a little clue that 7 maps to 2 as well. So 2 and 3 and 5 and 7. Oh, 2 and 3 and 5 and 7. They all map to 2. So 2 and 3 and 5 and 7 are our favourite examples. Well, not say favourite examples, but certainly our key examples of primes. Thank you, Nicolo. Thank you. So thanks, Doug. Number of factors. That was, I know this is not, this is kind of guess what's in my head teaching, which is not great teaching, but that's what I was thinking of. Number of factors. So that's really easy to say. So the position to term is really easy. So the position to term, it's the number of factors of n. That's really easy to say. Crikey, it's hard to work out. If I give you a 12-digit number, it might have 2 factors, it might be prime, it might have loads of factors. And of course, the term to term, well, again, the term to term is just impossible. There is no way of going from one number to the next number and knowing in particular whether the next number is prime or not. And so recognizing that the term to term is not only hard, it's actually impossible is a really good discussion, really good realization. Again, I think because they do a lot of work with linear sequences, in particular, and also quadratic sequences and geometric sequences, students tend to think that you can either always have term to term or position to term, and you've got one, you've got the other, and the whole thing's a bit simple. And something like this, I think, really exposes them the complexity of a sequence, which actually, nonetheless, is very, very simply, very easily defined. A couple more examples. I'll put these in basically for fun, actually. So 2, 4, 8, 16, 31, 57. So it looks like it's doubling. 2, 4, 8, 16, 32. No, 31, 57. So have I just made these numbers up? No, it comes from a very famous problem. So what it is if you have a circle and you join up, basically add on 1. So for 1, you have 2 dots. For 2, you have 3 dots on the circle. And it's the number of regions you make. So if you have 4 dots on the circle and you position them like that, say you can make 4 regions. The lines can cross, sorry, 8 regions, sorry. So there's your 4 and there's your 2. Okay, so what it is, it's sometimes called the pizza problem. I don't know why it's called the pizza problem. I'd be really naffed off if someone cut my pizza up like that. So essentially, it's the idea you put it's the position. One more than that is a number of dots, and then that number of dots goes on the circle, and it's the maximum number of parts that you can end up with. And try as hard as you like, you can't get 32. It's only 31, and 76 is nowhere near 64. It's 57. So it's just quite a nice example of, just because it looks like it starts doubling doesn't mean it carries on doubling. And there's a natural context to it. And of course, I can just run any numbers I like. I can just make up what's in my head sequence. But this has a natural context to it, which I think is really nice. And then the bottom one, 1, 2, 3, 4, 5, 7, I really have made up. But I want to introduce you to the OEIS, the Online Encyclopedia of Integer Sequences. Every mathematician's favorite book, the Online Encyclopedia of Integer Sequences. It's like Wikipedia, but just numbers. And when I send the slides to you, I hope you can see that's a link there. That blue thing there is a link. So you can click on it, and it'll take you to the Online Encyclopedia of Integer Sequences, and you'll see a page like that. And then you just type in, can you see, I just typed in 1, 2, 3, 4, 5, 7 and press search. And then I got 847 possibilities, 847 possible sequences, which start 1, 2, 3, 4, 5, 7, or actually contain 1, 2, 3, 4, 5, 7, and it's just astonishing. I mean, if you type the square numbers in, 1, 4, 9, 16, 25, you will get the square numbers, but I think there's about another 140 or so you also get. And so it is just this incredible repository of integer sequences. And a lot of them are quite obscure, but they are all well defined. They're not just random strings of numbers. They all have a problem, a context, a mathematical scenario which gives rise to them. So I think particularly actually at the moment, particularly in lockdown, tell your year 11s about this. Tell your top sets about the OEIS and just let them explore. Let them come back with you with their favourite integer sequence. And then I'm going to leave these two with you. Obviously, when you get the slides, you'll have them, or you can take, if you want to take a screenshot now, by all means do. So these are quite neat, and they have very nice position to term rules, but it's quite interesting to know what the term to term is. So I'm going to leave you to experiment those. If you get very frustrated, I want to know, email me later, and I might give you a hint. But these are not designed to be impossible, hence my Mr. Man. But again, it's just another set of examples to show your year 11s that sequences are not as simple as they think they are. Oh, sequences, yeah, no, it's like, like you find the difference and do the 0th term. No, sequences are much richer than year 11s often think they can be. I like these. I've built these as what they're called. Oh, sorry, Jenny's just said Bob, one of my favourites. Oh, Jenny, well, don't give the game away then. Jenny obviously knows the secret, but don't give it away yet. Right, these I think are quite fun. These are called arithmetico-geometric sequences. Arithmetico-geometric sequences. And the structure is you multiply and add. So here, I've multiplied by 3 and added 2. I've multiplied by 3 and I've added 2. I've multiplied by 3 and added 2. I've multiplied by 3 and added 2, etc. So the term to term is really easy. The term to term is really easy. Thinking of that is really hard, okay? And it's a really good bit of algebra for your students to try and work that one out. Do you want any suggestions? I'll just give you a couple of minutes. Do you want to think about the other two? Do you want to tell me what have I multiplied by and added? Either of them, I don't mind. Pop some suggestions in the chat if you want to. I like the bottom one, the third one, because it looks periodic. It looks like it's repeating 7 2 7 2 7 2. I mean, that's the idea. That is what it's doing. So then the question is, how can multiply and add do that? So Claire saying subtract 6, then divide by 2. Now, interestingly, Claire, I agree with you, but it's slightly the wrong way around. And if you look at the chat, folks, Claire and Henry are saying the same thing. They've just sort of said it the other way around. So the idea of arithmetico is you multiply first, but of course it's interchangeable. So yeah, you're right. I was thinking of multiply by half and then actually subtract 3. But of course that's the same as, and again, great activity in class. Well, is that the same as subtract 6, divide by 2? So are they the same? Is halving and then subtracting 3 the same as subtracting 6 and then dividing by 2? Or not? Yes, we know it is. Do your higher attainers. Now, then what about the bottom one? Any thoughts about the bottom one? And how might we go about exploring it? I mean, obviously we could set up an equation. We could do this algebraically. You know, we could say, we would make it times by A and add B. So we could say something like, so if you think of that, if we sort of thought of that pair, we could sort of say that 2 is, we could say that 2 is 7a plus b, and then we'd have to also then say that 7 is 2a plus b. And if you solve that, yes, Jenny, that's what I was thinking of. Thanks, Jenny. I was thinking of times by -1 and add 9. -7 plus 2. Sorry, plus 9 is 2, -2 plus 9 is 7, -7 plus 9 is 2, -2 plus 9 is 7. But how, getting that algebraically would be a good activity. And just a surprise, you sort of think if I'm adding and multiplying, surely they're going to get bigger or smaller. No, they can oscillate, they can stay constant. And then if you're going to do the algebra, and something like that, that's quite a nice algebraic problem to continue to explore. So just, yeah, I built the sequence and I pulled out the terms, and then I got them to think about it. So something like that. And then of course, that would be great for now make up your own. can they make up their own arithmetico sequences and share them with each other? Can they make up their own problems and share them with each other? Once they've got the idea, all the sort of intellectual activity involved in coming up with their own examples and coming up with their own problems like this, which have solutions, which have two solutions, which don't have no solution, that I think would be really worthwhile activity for them. Okay, so I promised you I'd talk about what's the same, what's different. So now I am. What's the same, what's different? So what do we notice here? We notice pretty much straight away that the first term, the first example is a term-to-term sequence. The first example is a term-to-term sequence. For example, is a term-to-term sequence, whereas the second one is a position-to-term sequence, because the value of that term depends on the value of the preceding term. So the first term is 3, the second term is 3 plus 5. The first term is 3, the second term is 3 plus 5, which is 8. The third term is 8 plus 5, which is 13. The next term is 13 plus 5, which is 18, and so on. And then this is a position to term sequence, and I meant to change this after yesterday. So you all just look away for a moment. I'm just going to scribble that out and write subtract 2. That's what I meant to write yesterday, and I forgot. And I meant to change it after yesterday's session. So now all look back. This is position to term, because this time the value of the term is given by the position in the sequence. One term to one position term, but as you see what I've done now, they generate the same values. So 5 subtract 1 is 3, 10 subtract 1 is 8, 15 subtract 1 is subtract 2 is 13. Sorry, 5 subtract 2 is 3, 10 subtract 2 is 8, 15 subtract 2 is 13, etc. So what's the same is they generate the same values. What's different is they do it in a different way. What about the next pair? Now these are both term to terms. But what happens? So we have 2, and then we double it and take away 1 to get 3, and then we double that and take away 1 and we get 7. And we double that and sorry, not 7, 5, and take away 1, and then we double that and take away 1 and we get 9, and then 17, and so on. Whereas here we get 1, and then we double it, take away 1 and get 1, and then we double that and take away 1 and get 1, and we double that and take away 1 and get 1. So the second one is a constant sequence, whereas the first one is getting bigger and bigger. It's diverging to infinity. So a tiny change, a sort of a very small change in this case of the initial values, has a very significant change in the behavior of the long-term behavior of the sequence. Whereas the second one, the last one, sorry, the third one. So we start off with 1, and now we're adding. So now it's double add 1, which is 3, double add 1, which is 7, double add 1, which is 15, etc. And then my position term formula. So the first term would be 2 to the power 1 subtract 1, which is 1. The second term would be 3. The third term would be 2 cubed take 1, which is 7. Ah, that's interesting. So they seem to be the same. So again, we have the situation whereby it seems that the position to term and the term to term are the same, and then perhaps try and work out why that's the case. So why, what happens if you double that and add 1? What happens? Do you get what you should get for the next term? So trying to explore why these are the same. It appears numerically that they are. Can we investigate whether that's true in general? Bring back to linear sequences. So again, this idea of what's same, what's different. Well, let's work out some values. So the first two say, well, they both start with 8. So that's 8, but then it's going up in 5. So it's 8, 13, 18, 23, 8, 13, 18, 23, 28, and so on. Whereas the second one it starts on 8, but goes with 3s. So 8, 11, 14, 17, 20, 23, 26, etc. Oh, but that's interesting because they've both got an 8 and they've both got a 23. Now, does that happen again? Is that a coincidence? Does it happen again? Do they have more terms in common? They clearly don't have all terms in common, but do they have more terms in common? What about 5n? Sorry. What about 5n take away 3? So that's going to be 2 and then 7 and then 12 and 17. And 22. Oh, that's interesting. Okay, so again, we seem to have something in common. does that happen again? Do these sort of sequences just sort of intersect at 17 and then go their separate ways, or is this going to happen again? Why do A and C appear to have nothing in common? 8 and 8 to 13. You look at the digit space, look at the pattern of digits, 8s and 3 for the last digits, 7 and 2 for the last digits. They're clearly not going to have anything in common, but can we explain why that's the case? What's happening for D? What's happening for D? So we've got 8, and then we've got 14, and then we've got 20, and then we've got 26. Change the colour. So we've got, 8 and 14 and 20 and 26 and 32 and so on. And so again, we seem to have some things in common. So we got the 14 and the 14 in common. We've got the 20 and the 20 in common. Oh, we've got the 18. Oh, that's interesting. So it seems to be that sort of every term in D is a term in B, but not vice versa. So some terms in B are terms in D. Every term in D is a term in B. And then what's happening with E? Happening in E. So we've got 44. So we've got 44 take away 6. So we've got 38, 32, 26, 20, 14, 8, 2, -4, etc. And so we can see that D and E have some terms in common. So they overlap for a bit, but then obviously the terms of D are getting larger and the terms of E are getting smaller. And so they, as I say, they kind of go their separate ways. So, a small set of formulae, do they recognize this? Do they ask these questions? Do they sort of go, I wonder if they recur again? I wonder if this pattern of intersection continues to happen. And if so, when does it happen? How often does it happen? Can we predict the next one? Can we predict how many there will be? So it's basically these sorts of questions. So when do linear sequences have no terms in common? When do they have lots of? So, and like for example, those two, A and B, it looks like A and B have got lots of terms in common. 8, 23, is there another one? When do they have all their terms in common? So the D and B situation. So every term in D is a term in B. So a term in D is always a term in B. A term in B is sometimes a term in D, using that always, sometimes, never language we talked about earlier. So those are the kind of questions that take you beyond procedural fluency and into conceptual understanding. And that seems to me exactly the sort of activity that students should be engaging with. So going from the fluency of working out an expression for the value of the nth term to the understanding of what is going on with different linear sequences and when do they intersect, when do they not intersect. And a really nice way of showing it is pictorially. So let's see if I can do this. No, that's not what I wanted to do. What I want to do is actually go into the slideshow, and then if I've set this up correctly, my finger works. Yes. Okay. So these are called Cuisenaire rods. And the website is actually, I hope you can see the top of the screen, it's called MathSpot. It's all free. It's just fantastic. And it's just a really good way of modeling sequences. So you think of the first sequence we had, began with 8 and went up in 5s. It went 8. And then if I'm just pressing on copy, I'm pressing on copy at the top, it just generates more 5s for me. And then my other sequence also began with 8. But went up in 3s. So they had the 8 in common. You can see they've got the 8 in common. And then it went up in 3s. And then suddenly, they've lined up. You can see how the end of the 5 and the end of the 3s are aligned. So 8 plus 15, i.e. 23, is the same as 8 plus 15, 23. 3 5s is the same as 5 3s. And so we can start to see that's why they are intersecting, because if I do another lot of 3 5s, what you do, if you sort of press on or click on the rod you want to copy and then press copy, it will copy across. And so then I do another 5 3s, then that also, you can see they've now aligned, they're now lined up, because 3 5s is the same as 5 3s. So these sequences will continue to intersect every 15. So the next one will be 38. The next one will be 53. The next one will be 68, and so on. And of course, what you're talking about here is lowest common multiples. And it's a really nice sort of sideways into lowest common multiples. It's a sort of surprise version of lowest common multiples. What happened with D? So sequence D began with 8 and went up in 6s, didn't it? It went 8, 16, and of course now it's really clear why B and D. You can see that every other term in the third sequence coincides with every term in the third sequence coincides with every other term in the second sequence. The end of a 6 rod coincides with the end of 2 3 rods. So you get a term which is in the sequence, a term which is not in the sequence, a term which is, a term which is not, a term which is, a term which is not. And these sorts of pictures really help students to explain what is going on with sequences. And then, of course, you can ask those questions about, when don't they overlap? So, we had the sequence which began with 2 and went up in 5s. So if I just copy the 5s, you can see that that sequence on top is never going to line up with the sequence underneath it. It's always going to be shifted back by 1. There's always going to be that shift. The gap is never going to change. So I think quiz and error rods are a fantastic way of really representing what is going on with linear sequences. I'm a big fan of them. So if I go back to my PowerPoint now, I'm just going to jump over these slides because I'm conscious of the time. I'll put a few notes on them when I send the PowerPoint to you, but essentially doing the same thing with linear and quadratic sequences. So when do linear and square numbers intersect? And then where do square and triangular numbers intersect? Are there any square numbers which are also triangular numbers? Are there any triangular numbers which are also square numbers? The answer is yes, and that leads on some nice mathematics. So I'll add some notes to those slides. Okay, Möbius sequences. Now, Möbius sequence, I know that looks really complicated. Sorry, it's partly because I wrote it yesterday without the brackets, and then it looked like Tn plus 1 over Tn plus 2, and that was really confusing. So I put the brackets in, but I'm not sure the brackets help enormously. So the idea is that you take your first value 3, and then your next term is going to be 3 plus 1 over 3 plus 2, i.e. 4/5, 0.8, and then your next term is going to be 1.8 over 2.8, which is something 9 over 14, not very nice, and then your next term is going to be that plus 1 over that plus 2, which is something, etc. So that's the idea behind this formula, is that you take a term, you add 1 to it, you add 2 to it, you divide them, and that gives you the value of the next term, and so on like that. And that's called, and a Möbius sequence is doing that in general. So as you can see at the top, A, B, C, and D are constants. So A, B, C, D are constants. And I've chosen a really simple case here with A being 1 and C being 1 and B being 1 and D being 2. But actually it's not that simple. I mean, even just trying this simple expression, but the different starting values. So you start with 0, start with -3, start with -2, that's going to be a bit of a problem, isn't it? Because you're going to be dividing by 0, so a bit of an alarm bell there. So what happens if you start there with -1.99? You're basically dividing by something very near 0. So what happens? Well, the answer gets huge. You're going to be suddenly get a very, very big answer for the next term. But then what happens? Well, then you're going to have a big number plus 1 over a big number plus 2. So basically going to come back down to a small number. So your second term is going to be dividing by 0.01. So it's going to be 990. No, sorry, 99. It's going to be 99. And then it's going to be 99 plus 1 over 99 plus 2 is going to bring you back down to small numbers. And so experimenting using calculator or a spreadsheet, experimenting that I think is a really good activity for the students, just to realize that sequences can jump around all over the place, and then they might not. This iteration might do something. It might say converge to a value. So experiment with iterations. Now, what becomes really interesting, though, is if you choose them carefully, and I'll give you a hint about what I mean by carefully, you can get very interesting behavior. So if I start here with 3, then my next value is going to be 3 plus 1 over 3 take away 1, which is 4 over 2, which is 2. And then my next value is 2 plus 1 over 2 take away 1, which is 3. So this sequence, so starting with 3, is periodic. So it's 3, 2, 3, 2, 3, 2, 3, 2. Now, I will let you play around with these yourselves. Something similar happens with B and C. So B and C have similar behavior. They don't oscillate quite as straightforwardly as 3, 2, 3, 2, but they do something interesting. And again, it's the same idea about the simple formulas, simple changes producing surprising behavior. Now, of course, just because it's true for 3 doesn't mean it's true for in general. So let's do the algebra. So we're going to start with A, and then my next term is going to be A plus 1 over A subtract 1, and then my next term is going to be A plus 1 over A subtract 1 plus 1 over A plus 1 over A subtract 1 subtract 1. Now, what's that the same as? And for your higher attainers, for your top set, you can absolutely see the value of that algebraic simplification. This is algebra for a purpose. You're not just doing an exercise in algebra because the textbook says so. You're actually trying to prove something. You're really sure. You've seen numerically it goes 3, 2, 3, 2, 3, 2. So you're really sure this goes A something. So you're really expecting this to be A. So you kind of know where you're heading, which is quite encouraging. But does it work like that? And then, of course, doing the other ones as well, doing all the other ones. So considering what happens for those cases. So you've tried it with 3 numerically, you can try it therefore. So Nicola, you've asked about doing graphically. I wouldn't with year 11. I think to do it graphically requires a real sophisticated understanding of what graphs are saying and how to interpret graphs. And I think that's quite sophisticated for higher attainers. Even for higher attainers in year 11. I think that's definitely a sixth form idea. Whereas algebra, I think it's just really good algebra practice. This is like doing a good circuit training. This is like doing what's it called, a HIIT class, HIIT, high impact interval training or high intensity interval training. This is a real workout for the algebra muscles to prove something they've discovered to prove something they've discovered numerically, or they believe numerically. And then in general, my hint for you is it's worth investigating sequences where you like this. So e.g., so 2tn plus 3 over tn subtract 2, where your coefficient in the numerator is the negative of the constant term in the denominator. And my suggestion is it's worth experimenting with that and seeing what happens. Sequences of that form have a property, and you can prove it in the same way that you've proved the previous cases. Now, I'm conscious it's past. I've got 5 more slides, which I'm going to talk through quite quickly, even more quickly than the previous slides. If you need to go, please go. I will send the slides to you as soon as I can afterwards. So a quick pause. If you need to go, thank you so much for your time. Hopefully see you again next week, if you can make it. If you can hang on for 4 minutes, 5 minutes, I will zip through the remaining slides. So functions. I just chose those functions. Just remind about compositional functions. Make sure they can tell you that f of x doesn't mean it is not x plus 2 squared. That would be fx multiplied by fx. That's not what we mean. What we mean is f of x plus 2, which is x plus 4, and then fh. So f of h is x squared plus 2, and why I wrote g there. And h of f is x plus 2 all squared. And then GGG is 2 of 2 of 2x. And they will say 6x. If you put this in front of them, they will say 6x, because 3 2's make 6. Somebody will say 6x. Oh, it's not, it's 8x. And then I must admit, I like going backwards. I like going the other way around. So what would give you those? So if you've done the composition like that, if you've done the sequence of functions one way around, go the other way around. And that's definitely one of my sort of a catchphrases, is forwards, backwards. So this is the backwards, and that was the forwards. Here's the composition. What's the answer? Here's the answer. What was the composition? So obviously that is going to be f of x, 4x squared. Well, that sounds. Oops, sorry. That sounds to me like h of g. Sounds to me like 2x all squared. And so then, how do we get that? Well, that looks like g of h of h. I've got a square and then square again. Actually, no, that would only give me double, wouldn't it? Yeah, no, it's definitely not that. Right, okay. I should try and do these things off the cuff. It's going to, sorry, my hand keeps pressing the wrong part of my PowerPoint. So that one there, so that is going to be my g of h, my 2 of x squared, and then this is the square of that. So this is going to be hg of h. And that sort of reasoning, building up those backwards. Here's the answer, what's the composition? And then in terms of sequences, just thinking about the sequence f, ff, fff, and then so on, f to the power of n. So we'd have x plus 2, x plus 2 plus 2, x plus 2 plus 2 plus 2, etc. So what might that be in general? And then we'd have 2 of x, and then 2 of 2 of x, and then 2 of 2 of 2 of x, and then what would that be in general? And then we're going to have the x squared, and then the square of x squared, and then the square of x squared squared, etc. And just coming up with algebraic expressions for each of those. And then if you want to do something like this, here are 3 functions which are very nice. I've chosen them so that when you work out the sequences, they're nice to do so. So you get interesting behavior here when you iterate them repeatedly. And then you can do the same thing if you like the backwards. So there is the forwards. Here's the composition, what's the answer? And then here's the backwards, here's the answer, what was the composition? How do you get those? And again, of course, what next? Now make up your own. Make up your own and swap with each other. Can you make up one which your peers, your friends in the class can't solve, but you can? Can you make up one which is correct, but which your friends can't work out? And I think those sorts of activities, again, if they can do that, they really understand composition and sequentiation of functions. So you'll be delighted. I'm going to pause there. I'm going to shut up there. I'm very happy to take any questions you've got. Some. I'm also very happy to go because I have completely overrun my time, for which I apologise. I will send you the slides. I hope it's been of use. I hope it's been of interest. I hope, I said I want to try and inspire and infuse and show you some ideas which intrigue you. I hope I've done at least some of each of those. And I hope you'll be able to join me either next week or for one of the others. Thank you very much for your time and all your contributions. Bye for now. If you've got a question, just sort of hang on a moment. What I'm going to do is I'm going to stop sharing. Turn off my video because you feedback forms. I need to send you the link to those. Sorry, someone just asked me about the feedback form. I will send you the link for that a bit later. Right. So that's my iPad turned off, so you don't have to stare at my nose because so people who are, if you could say someone who was Yuvraj, you said you had a question. Do you want to speak up?
Hi, Niccolo here. Sorry.
Hi, Niccolo. Yeah. Hi.
It's a very quick one. I've never taught year 11.
Sorry, can I just turn my volume up?
I've taught all the year groups, but not year 11, and I usually teach just A levels. So I've got a year 10 class, a top set, and I was thinking about this as possible, stretches. But I was wondering, would you use this in a usual class, or would you actually set up like an afternoon club or some stretch?
No, good question. This is all stuff taken from lessons. No, I mean, obviously we've gone through it really quickly. There's about 5 lessons worth of material, and we've done it in an hour. So there's far too much for one lesson. But all this stuff is taken from lessons. I would do a whole lesson, or possibly even a whole 2 lessons on just those tables, because what I want them to do is I want them to say, well, I think it's this. Well, I think it's that. Well, I think it's this. Well, I think it's that. Well, let's decide. Let's agree. Let's convince ourselves.
I guess that pretty much like. All of it from the 20th minute onwards is non-examinable because it's not going to be in a GCSE paper.
No, so, but remember what I said. Fair point. Remember what I said at the beginning. we're trying to develop their procedural fluency and their conceptual understanding. So we're looking for context to make them do more algebra. Remember what I said about the Möbius functions? Yeah, the Möbius functions are not in the GC paper, but that algebraic simplification, algebraic simplification is, so what you want is a context to make them practice simplifying algebra. And that's, that the Möbius functions is a way.
Absolutely. I'm all about practicing for the sake of practice, not just for the sake of the exam. Absolutely. So like what was evident for me after the session and probably reminded me is that these are good examples of how you can develop more than one skill while doing one topic. You actually tap into several more. So
exactly, yeah. And even the arithmetic geometric sequences, that's basically an excuse to come up with some simultaneous equations and solve them. It's just a context to simultaneous equations, but it's a context they won't have seen before. So part of the excitement, part of the challenge of teaching higher retainers is getting them to practice skills in a way that they don't think they're practicing skills.
Take a note of that. Thank you very much. That was all for my questions. Thank you.
Okay, thanks.